This is Mike Houston.
So the first thing we're going to show you is deep neural networks doing some of the traditional computer vision techniques that you've seen. So in this case, we're actually going to detect crosswalk signs. So you see that we pulled this crosswalk sign. So again, the interesting thing here, as opposed to trying to train something like a hog detector, histogram-oriented gradients, to recognize the diamond, we've just given lots and lots of examples of crosswalks as a tag for the neural network to learn. What's interesting about this technique, compared to traditional computer vision techniques, is the distance and accuracy at which we can detect things. So there's another crosswalk sign coming up that's very far away, right at the edge of what you would naturally be able to see to begin reacting to. So in a case like this, especially if it's busy and you're at high speed, this can feed back into the ADAS system to change your situational awareness, i.e. slow down even below the speed limits if you know that it's a busy pedestrian area. This is actually around the San Jose courthouse. The more difficult ones, as Jensen mentioned, which is occluded pedestrians. So if you notice, behind that police car, there's a partially occluded pedestrian. And it turns out it's actually a bicyclist. So we see occlusion, we can't see the bicycle, and so we tag it as a pedestrian. And then as soon as we can see the bicycle, it gets redetected and reclassified as a cyclist. So one of the things we can do is detect street lamps.
Mike, before you go on,
sure.
For most people who are watching this, of course, this is computer vision. The video was obviously recorded a priori. Okay, the video is not live, obviously, but the processing is done live here. The video is going into the Tegra chip, and the Tegra chip has a deep neural network that has been downloaded to it, and it's been trained to recognize a handful of things in this particular case. Okay, so whenever there's a video, whenever there's an image that comes in to TX1 and has one of those objects that it has been trained to recognize, in this particular case, and just some of the cases, and we'll show you a few more really cool ones, even an included pedestrian, it would recognize it. So the video is not live, but the processing is done live. Go ahead, Mike.
So in this case, you see that it understands that the left turn lane is actually a red signal, and that forward traffic can proceed because the signals are green.
And so, in this particular case, stop there for just a second. In this particular case, really what's really super cool is this. It's a bunch of lights. You know, it's a bunch of red and green lights. However, once it recognizes, detects them, and understands and classifies a particular light, it can also
classify it to let you know there's a speed camera here.
Well, that's probably the most valuable detection you can imagine.
So we've been able to read that this is a 50 limit speed sign. What's particularly difficult actually about these signs is they have an update refresh interval of 60 hertz, and we're driving a 30 hertz camera, so they actually blank out. There's certain frames that actually doesn't have a complete representation of the sign. The other note here is this warning on the left. It says Q. So what this means is there's congestion ahead that you're going to need to slow down. That's awfully important information if you're traveling at high speed. So as we continue down the road.
Now if you could just pause for just a second. Just right now you saw 4 objects classified in one scene. There were already 4 classes right there. It's one gantry, but there was a speed, there was a camera alert. There was also the fact that there was going to be congestion up front. Okay, there were already multiple things that were being classified. Keep going.
So as we continue going, we begin to get congestion. A couple of things begin to happen. So we actually begin to pick up and recognize that there's actually braking traffic ahead. So if you notice, there's one car that's beginning to brake because the traffic is slowed in front of them. As we continue to close, we begin to get more triggers. So as opposed to relying on a radar system or something else or a collision avoidance system, you can actually detect that there's upcoming traffic and braking that's required. So you can get to smoother stops without harsh stops. All right,
That's not too bad.
So why don't we go to Vegas? So one of the other things we can do is In this specific case, we're doing vehicle detection. And so we can actually subclass vehicles down. So you can make different driving decisions based on the class of vehicle that you have. So in this case, we're classifying the vehicle, so you can see there's two SUVs in front of us. The bar on the bottom represents the confidence level. This is how strong the neural network believes that what it's saying is this class. So it's driving by the wind. So you see that we have a passenger car tagged there on the left. An interesting thing happens as we close on this intersection. So we begin to get a strong number of detections. And we still have the two SUVs that we tracked in front of us. We've now picked up a heavy truck on our right. It's actually one of these advertisement trucks you guys see driving around here. An SUV. On the other side, we have a truck and a van. So a few frames ago, probably went by too quick, but you guys can see it on the hands-on. It actually classified that hotel transport van as a heavy truck because it had just this base initial view.
So one of the challenges with computer vision is that it requires real cameras and rigging up of situations and cameras on vehicles and other things if you want to test real autonomous driving types algorithms. And a lot of times that configuration is challenging. So what we thought is, why not do it in a virtual world? Especially since we have such expertise in realistic rendering and photorealistic rendering and physically based rendering, we developed this simulator to do exactly that. So this is a parking garage that's based on the parking garage at NVIDIA headquarters in Santa Clara, California. And Curtis here is going to drive the car around this environment to give you a feeling for what the space looks like.
Now remember, this is completely real-time 3D. This particular parking garage is real. It is really our parking garage.
So in addition to driving through it, Curtis can change the configuration of which spots are filled and what cars are in the spots. And indeed, we can actually even just fly around in the environment, fully real time, and click on the spots and reconfigure them to different vehicles, or even make the spot completely empty, or whatever you like. Okay. So this is the first part, which is the actual simulator. So another component of the simulator is it's not enough just to render this viewpoint, but we also need to generate inputs that would run into computer vision algorithms, and that means we got to attach cameras to this car. So let's transition to the other visualization. So what this is showing here, the center image is running on the same machine that you were just seeing. The four images around it represent the views from different cameras that are attached to this virtual environment. The next part of the demo, what we're going to show is, given this data that the simulating environment generates, which is the fisheye input camera inputs, we're going to show some computer vision algorithms on which we'll base the Drive PX features. So what this visualization shows on the left, we've got 4 camera inputs. Those are generated in the simulated environment. It will look familiar to you. It's the parking garage we just showed. On the right is one of the surround vision visualization modes we have, which takes the 4 camera inputs and warps them to show a simulated top-down view. I'll let this run a little bit, and you can see as we move around through this environment, the camera's updating as you'd expect. So one of the first visualizations I'm going to show is what's called feature tracking. So this is a computer vision algorithm that basically identifies salient points in the images. So this is all just in 2D. And what it does is basically tracks them from frame to frame. So this is an important building block in doing computer vision, because it allows you to actually know that a point from one frame to the next, how it moves from frame to frame. So what we can do if we have that visual, once we've done the actual frame, the actual feature tracking in the 2D, is we can switch to...
Jim, don't switch it.
Okay.
So what you saw, does that make sense? Previously, the previous scene was a simulation of the parking garage. Now, that simulation turns into video input, and you're now looking at all of the data that's being processed on the Drive PX.
That's right. So we can advance it a little bit more, and then switch into what we call point cloud mode. So what this shows is, given the features that are tracked in the 2D images, what this does is in real time, using CUDA, based on both of those features and their positions in the images and the poses of the cameras, which we determine algorithmically, reconstruct the 3D positions of the actual geometry in the scene. So if I pause it for a second, like right here, for example, I can actually rotate around this in real time, and it gives you a sense for the points in the scene and the structure of the environment around the car. display it here a little more. So this is an important building block because what we need is for the algorithms that happen after this, the real sort of intelligence and reasoning about the surroundings types of algorithms, we need them to know the structure of the environment so they can navigate, they can make decisions about where to go. And so the first step to that is generating the actual, a sense for the actual 3D geometry of the scene around the vehicle.
And so what you're looking at here, number one, we're modeling the environment. We're also understanding what we see. And now, as you saw, we're doing pathfinding. Okay, go ahead.
Okay, yeah, and if you're curious here, the colors, by the way, are basically indicate which camera of those points came from originally. But they're all in the same 3D space. Okay, so that's what's called structure for motion. It's a very important fundamental algorithm in computer vision. And then the last step, the last thing we're going to show everyone is basically putting all of these pieces together. So what we see here, the image on the left is the simulator image that we showed initially, the same environment. What we showed earlier when we were showing the simulator was actually being driven by a human. We were driving around just using a keyboard. Now what we're doing is we're taking the images that we're generating by those 5 servers that Jensen talks about, sending them actually over a network to a client, which is doing the computer vision processing, analyzing the images, doing structure for motion
on the car. Okay? The only thing that's being done in the server is the simulation and generating what is essentially virtual video input that comes into Drive PX.
Exactly. So let's go ahead and try to find a parking spot. So what you see on the right, and the right side of the right, are again those images, and that's the only information that the pathfinding algorithms and the computer vision algorithms have about the world around them. Right? So the server generates those, the simulator generates those. Some reasoning is done on those images. 3D points are generated, so we understand the structure of the environment around the car, and then we can determine where to go and where not to go based on that 3D structure. So another visualization we have here, you can enable the obstacle map. This is something we call an obstacle map. This is showing basically, given the 3D points that we showed earlier from the point cloud, we can actually do some further reasoning about that, where we determine which of those points correspond with obstacles, things which are undrivable, and which ones are not. Which ones are things like the floor, the ceiling, the parking garage, things which are not obstacles and so can be driven on. And so what we see here is, as the car navigates the space, the green line is the path that the car is following. The red points, areas of more red density are areas with more obstacles in them, and so there are places that we cannot go. And additionally, one visualization you're about to see now, because we found a parking spot here. You see there's an empty parking spot on the right. It's determined that it's a parking spot, because there's 2 sets of criteria that we need for determining if something is parkable. One is that it has no obstacles in it, and the second is that it is actually a parking spot. Right? We don't want to park in the middle of the garage where there's no parking spot. And so a parking command and a parking algorithm is executed, and we successfully park in the parking spot.